I'm Prof and welcome to Chemistry Matters. And today we are going to talk a little bit more about the fundamentals of acid-base chemistry. So in the previous video we talked about the very fundamentals of acids and bases, the fact that we're going to define the acid as being a proton donor, a base being a proton acceptor, okay? And we looked at the simplest possible acid-base reaction, essentially the reaction of H2O plus H2O in equilibrium with H3O plus OH minus. Okay, this pure liquid, aqueous species, and aqueous species. Now, one thing that we didn't talk about in this reaction was to show that it's actually an acid-base reaction, okay? Because in an acid-base reaction, we have one species acting as an acid, being a proton donor, the other species acting as a base, being a proton acceptor. And so let's have a look at that in this case. So we're going to say that this is going to be an acid. This is going to donate one of its protons to this molecule of water, which is then going to act as the base. Okay? So this donates a proton to this. The net result of that is formation of H3O plus, the hydronium ion, and the OH minus ion. Now, a little bit of thought hopefully will convince you that if the forward reaction involves the transfer of a single proton from an acid to a base, then the reverse reaction must also involve the transfer of a single proton from an acid to a base. You can see here, this is going to act as an acid and donate a proton to OH minus to get the reverse reaction going and give you 2 moles of water. Now this has a special name. This is certainly an acid. It is called the conjugate acid. And this one is a base. It has a special name, a conjugate base. Okay. So on both sides of an acid-base reaction, you have got an acid and a base. And now these guys are related by differing by a proton. An acid will lose a proton and become its conjugate base. A base will gain a proton and become its conjugate acid. So that's what we're going to have. We're going to have 2 conjugate acid-base pairs in any acid-base reaction. Okay? So we're going to have 2 species on either side of the equilibrium arrow. One's an acid, one's a base, one's an acid, one's a base, and they are related as conjugates, and they differ by a single proton. Okay? So that's a little bit of terminology for you. Okay, so let's get away from the simplest possible acid-base reaction, and now let's talk a little bit about the strength of acids. And again, you probably have this idea of taking an acid, getting this liquid acid out of a bottle, pouring it on something, and it just burning a hole through whatever it is that you pour it on, okay? It's not quite like that really, but some acids are very good at doing that sort of thing. They will react quite vigorously with metals, for example. Other acids, you can sit there and look for literally years and no such reaction obviously occurs. So some acids are strong, what we call strong, and some acids are weak, okay? And in fact, most acids, the vast majority of acids are in fact weak acids. There are very few strong acids, okay? And strong acids, what's the definition of a strong acid? So a strong acid, we would say a definition of that is one that dissociates completely in water. So in other words, a strong acid will donate its proton completely to water, okay? So what are some examples of strong acids that you may have heard of? Well, things like hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3. They're probably the three biggies in terms of strong acids. Acids that when you put them in water will donate a proton completely to water. What else have we got? We've got HBr is another strong acid, hydrobromic, HClO4, perchloric, that's a strong acid. And if we want to get really exotic, we could go CF3SO3H, trifluoromethane sulfonic acid. Try saying that 10 times fast. Anyway, these acids all have in common that they are strong acids, and if we put them in water, acid HX plus H2O, they will react completely, not in equilibrium anymore, they will react completely to form X minus plus H3O plus. Okay, that's your definition of a strong acid. So, strong acids, as I say, there's not really many of them, but a really good thing about strong acids is that we can do relatively straightforward stoichiometric calculations with these. And that's always nice. And the reason that we can do stoichiometric calculations with these is precisely because of the fact that they react with water to completion. So let's do an example. Let's take a solution of HCl. Okay, so we've got aqueous solution of hydrochloric acid, and it is 0.125 mole per litre concentration. Okay, what is the pH of this solution? Okay, so the first thing that we need to do really, like a lot of problems, is when they involve stoichiometry, balanced chemical equation. Okay, so what's your balanced chemical equation here? HCl plus H2O goes completely to, reacts completely to give H3O plus Cl minus, aqueous, etc., etc. Okay, and we'll say that's a liquid there. Okay, so in other words, we're saying this is a stoichiometric reaction that if we start off with 1 mole of HCl, we're going to finish up with 1 mole of H3O plus. Okay, so therefore, what's the pH? Well, we know our definition of pH is negative log of the H3O plus concentration. Now, do we know the H3O plus concentration here? Well, yeah, we do. And the reason that we do is because we know our HCl concentration is 0.125 mole per litre. We know that the HCl reacts completely to give you H3O plus, stoichiometric amounts of H3O plus, and so therefore the H3O plus concentration in this particular solution is going to be 0.125 mole per litre. So therefore the pH of this solution is going to be the negative log of 0.125 mole per litre, and that then comes out at 0.90. Okay, so a pH of less than 1. That means that that is a pretty acidic solution, and it undergoes complete dissociation to make it so acidic. Okay, so that's what happens when we're talking about strong acids. So strong acids protonate water completely. Now, obviously, when we're talking about strong acids, we should also talk about strong bases as well. And surprise, surprise, strong bases deprotonate water completely. What are our examples of strong bases? Well, in fact, there aren't many strong bases at all. And pretty much they all involve the hydroxide ion. So we would talk sodium hydroxide, we would talk potassium hydroxide, lithium hydroxide, maybe calcium hydroxide, etc., etc. Anything that gives rise to stoichiometric amounts of hydroxide ion when you dissolve it in solution. Okay, So, let's again do a little calculation and say, right, we've got a solution of sodium hydroxide and the concentration of the sodium hydroxide is equal to 0.250 mole per litre. Okay, what is the pH? So what's the pH of that solution? Now, this is a little trick to this now. pH is all to do with the H3O plus concentration, isn't it? It's the negative log of the H3O plus concentration. But what we have here is an OH minus concentration, not an H3O plus concentration. And so therefore we are going to introduce this thing called POH. And P, we didn't point this out before, but P just means take the negative log of. So POH is equal to the negative log of the OH minus concentration. Okay? So we can quite easily get a POH of this solution. We're saying, right, we're putting sodium hydroxide into water. Our balanced chemical equation for that would be NaOH, solid, dissociating completely to give Na plus aqueous plus OH minus aqueous. Okay, this reaction goes to completion, and so therefore our 0.250 mole per litre solution of sodium hydroxide is going to have an OH minus concentration of 0.250 mole per litre. So in this case, our OH minus concentration equals 0.250 mole per litre. So therefore, our POH is equal to the negative log of 0.250, and that then is equal to 0.60. But that's not what the question asked. The question asked what is the pH of this solution, not what is the POH. How do we get the pH from the POH? Well, here's an equation that you'll probably need to remember, is that pH plus POH is equal to 14.0 at, all importantly, 25 degrees Celsius. Okay, so that's the relationship between pH and POH. So, relatively straightforward then, we can say that the pH of this solution is going to be 14.0 minus 0.60, and that's going to be equal to 13.4. Okay, so that's your pH, a very basic pH. Okay, much higher than 7, quite close to 14. So, strong acids, strong bases. So when you're doing calculations with strong acids and strong bases, we find that the calculations are governed by good old stoichiometry. Okay? And you assume that the reaction of your acid with water goes to completion, or that the reaction of your base with water goes to completion. You get stoichiometric amounts of either H3O plus or OH minus. You then play around with some negative logs here and there, and you end up with either your pH or your POH. Okay? So, nice, relatively straightforward calculations involved with strong acids and strong bases. So I'm sure you like nice, sort of straightforward, relatively easy calculations. Certainly get those with strong acids, strong bases. We will find that the situation with weak acids and weak bases is perhaps not so straightforward. Okay, that's enough for the moment, and we will see you in the next video.